Yeah, so you guys heard from me some yesterday. I'm hoping today's talk is a little more science and a little less tedium. So a few people have mentioned the Surrogate Hessian method for optimizing structures in diffusion Monte Carlo, and I'd like to outline in a bit more detail what this method is, how it works, and what motivates it. So just as an overall motivation, why do you care so much? And I'll use 2D materials as a class of materials to motivate why you really want to care about the structure. So quasi 2D materials can show extreme amounts of structural sensitivity. So for example, there are low energy modes that can result in large variations in the structure. Some common phenotypes here in like black phosphorus and stannine analogs, arsenic and polymorphs, you have these corrugated structures. And sometimes the 2D material is much kind of stretchy in one direction and stiff in some others. Or in the TMDs, you have these kind of low energy distortions, this 1T prime distortion. And these low energy modes, these stretching modes that result in large structural variations, can also are sensitive to the chemical environment, one, but also since you have these low energy modes, the resulting structure can also be sensitive to approximations in theory. So exactly when you have systems where low energy scales matter, those are the same systems where DFT may be expected to struggle and where you may want to bring a many-body method into play, like diffusion Monte Carlo. And this has consequences because these structural variations in these systems will often couple strongly to physical properties, whether it's magnetic coupling or optical properties, the band gap, et cetera. So getting the structure right can necessarily be a necessary prerequisite for even getting the properties right. So of course, DMCs you might want to use to get a high quality PES. And I'd say the main approach in quantum Monte Carlo to date to attempt to relax structures is following on from a lot of the approaches in the DFT and other communities to use forces, right? But in quantum Monte Carlo, forces I think are still approximate at the level of VMC or VMC plus, right? And some downsides are that the statistical distributions can be ill-behaved, or at least you need to work hard to tame. So in this work, I propose to combine cheap but informative Hessian information along with a mode decomposed energy fitting. So why might you want to do this? So to motivate this, I kind of show just a schematic of order of information that you might obtain from the local PES. The lowest order of information, of course, is just an energy value, a value at a single point. It really doesn't contain any information about the potential energy surface nearby, and you'd have to just sample many, many, many points in order to build up some type of information about the potential energy surface. Higher order information is contained in the force, right, which essentially gives you a plane, more or less, of information about what the local PS looks like. But higher order information is embedded in the Hessian, right? So if you could get full information about the Hessian, you might actually be able to get to your relaxed structure faster, in fewer calculations than with the force, because you have in a more information-rich environment. Okay, but I said I'm mixing the energy Hessian information with energy value information. Okay, and particularly not an exact energy Hessian, but an approximate one. So on one hand, you have an energy Hessian. It contains approximately the right information. You combine this with energy values, and you're left with this question, is this better or worse than using forces? There's reason to believe that it might be competitive with forces, but the advantage can be twofold. So the approximate energy Hessian that I use information from comes from a surrogate theory, like diffusion density functional theory. DFT is often pretty close, right? You're not miles away from the mark. You're some percents away from the mark, 3%, maybe 10%. Right? And so it still contains a lot of useful information. While sampling energy values, using diffusion Monte Carlo. So that's approximation free. You will arrive at the DMC minimum, not VMC or some approximation to DMC, and still get there in a way that's efficient. Okay, so So some advantages to this is that you don't really have to do much coding because this wraps around just traditional DMC energy evaluation. It makes efficient use of Hessian information you can get from other theories. You could do it from DFT, but you can also get it from MP2, whatever your favorite electronic structure method is that you feel is cheap enough compared to the heavier quantum Monte Carlo, and you can get Hessian information out. The method is developed that I'll go through in more detail about allows for mode adaptation of the statistics to enhance the efficiency. And built-in control for systematic and statistical biases. You get to impose a requested tolerance on the parameters, the structural parameters, and the method accommodates that. Another nice feature is that you can relax more than just in the internal parameters and your crystal structure. It automatically, you can build in or use cell degrees of freedom just as naturally. So variable cell relaxation is not really any more challenging. Okay. So what information is used? Well, we don't use the full Hessian information from DFT. Particularly, we use these special directions which DFT identifies. So the Hessian gives you this elliptic paraboloid here. And these directions in descent methods are known as conjugate directions. And so you can have an efficient descent. So what does that look like? Well, if you imagine that you have your energy, your PES, as a function of the structural parameters, you expand it to second order and you get a parabolic surface. If you're just doing this with energies, you might need something like m squared energy points, where m is the number of parameters you're attempting to optimize. You can break it down into mode decomposition, just diagonalize the Hessian here, and you automatically get this decomposed sum over these special coordinates, which are now decomposed lines. So you only need about 6m energy evaluation, something smaller. Okay, so that's a relationship between these, just your overall natural space and these conjugate directions. The conjugate directions are where you gain the information from the DFT or the surrogate theory. And then after that, it's up to you to make the most efficient use of the energies that you can. And most of the rest of the talk, I'll be describing how you make the most efficient use of the diffusion Monte Carlo information. But to give an idea of how the method works, it's a parallel line search method. And so these contours here, I'm representing a potential energy surface. You start from the relaxed DFT structure, and these are the conjugate directions coming from the DFT Hessian. So imagining that those directions were exact, the nature of conjugate directions in line search is that if you performed a scan along each one of these lines and found the minimum along each one of these lines, it's represented by the red dot, and then you simultaneously updated the parameters from each of these line scans, you will land exactly in the minimum of the PES. So if the directions are perfect and you're in the quadratic regime, you can converge in a single step. If your directions are not perfect, then you're going to have more than one iteration. In practice, you'll see there have been a number of cases we've tried for diffusion Monte Carlo. It requires about 2 iterations, so it's really quite fast. Okay, so overall, like I said, this is in the family of conjugate direction methods. And what we're going to do in these next cases is use information about these from the surrogate theory along these different lines to give you information about how you should construct the line search and the statistical properties of the method. So you've essentially reduced the problem from this high dimensional problem to many repeated single dimensional problems. And so I'm going to transfer now just to that single dimensional problem where you're actually going to do diffusion Monte Carlo at a certain number of points along a line scan. And now you have questions to answer. You want to know how far you can do your line scan on, how many points you want to use, what type of statistical resolution you need, right? Because that makes a big difference. If you just, take out a giant hammer and say, well, I'm going to run this to sub-millihartree error bars on everything, you might be paying 10s or even 100 times more than you need to. And that's an important thing to accommodate for. Okay, so how do you do that? So in the method, we use the surrogate to give us a slice through the PES. And then imagine doing successive energy windows that sets this kind of grid extent that you're going to do a line search on. So you have two parameters. One is how high on the PES you're going to climb, setting your grid extent, how far you're going to do a line scan through. And the other is the value of the statistical noise, which you're going to employ as a target for the energy in DMC. So those are two parameters, right? And you can imagine as you took, say, a polynomial form and fit the statistical curve, each different fluctuation here in the error that you get, you're going to create a whole distribution of minima, right? And what you want to control now is your confidence interval on how far away this distribution is from your target to be able to control the error. So for example, this can be a probability distribution representing the fluctuations in the minimum. And you want to say with 95% confidence, I am, say, within 0.01 angstrom for that parameter, right? Okay. Once you've set the constraint that you're within, say, 0.01 angstrom of the answer you want to be, then you have some choices that you can make, right? That's a constraint. Now you have an additional degree of freedom because there are two parameters, right? The grid extent and the noise. And so what you want to do is you want to increase the amount of statistical noise you can tolerate without exceeding that constraint. So what we actually do inside the code before any DMC is run, just based on the surrogate, is we build up a surface like this based on the 95th percentile of this confidence interval. This forms a 2D sheet where you have this kind of window size and statistical noise. You say, I want to match this tolerance that sets a contour on this surface, and you can just scan the grid extent to maximize the statistical noise that remains within your tolerance. So this line is the whole set of solutions that is within your tolerated noise that you as a user set, 0.01 angstrom. And here we've maximized the type of noise. And you can see that an arbitrary choice, something smaller, say a 0.02 in this units for sigma versus 0.04, is a factor of 4 savings in the statistics. That matters an awful lot in DMC. And this changes mode by mode. So this mode here has a particular curvature. High curvature modes generally cost less. Those would be like stiff bonds, like a carbon-carbon bond. It costs a lot less to resolve that to 0.01 angstrom. If you've got a carbon-hydrogen bond or other things, right, that are much looser, then you're just going to naturally pay more. But handling it mode by mode allows you to optimize, spend the extra effort where it matters and not spend it where it doesn't. Okay, and in that way, you can maximize the information you get out of diffusion Monte Carlo. You can also use the same approach to optimize what type of function you should fit along each line. So here I'm just showing some results for cubic, quartic, and quadratic functions in terms of the maximum tolerable noise and in terms of the maximum search range that you can get. So you imagine if you just chose, well, let's just use fit quadratics along each search direction. Well, you can't tolerate very much noise, right? So this is a parameter target. This is your target that you want, say 0.01 Bohr. You can only tolerate this much noise using a quadratic. Furthermore, you can't extend your line search very far before the systematic errors come to get you. So I've talked partly about the stochastic errors, but this includes the combination of statistical and systematic errors. You can't exceed either. And quadratics often will not fit the local PS well enough. You go far enough out, they'll diverge from it. Cubics and quartics, of course, have much more flexibility. So a quartic function, for example, you can reach much farther. You can describe a much larger range of the PS accurately. But as you add more degrees of freedom, you actually start to lose information. You introduce wiggles into this thing you've cut PS through. And so it turns out cubics are the things that win. You get a larger search range and they can tolerate a lot of noise. And so that's essentially what we use. We just use the method to select the type of form you can use, and we proceed with cubics generally. to gain a much larger efficiency gain. So you can see here again, you can tolerate 2 or you can tolerate 9. You get something like 10x efficiency gain just by selecting the right polynomial to fit.
Question.
Yeah.
Did you look at fifth order by any chance?
So we've looked at them in other contexts, fifth and sixth. So some of this came from looking at higher order polynomials when looking at VMC forces with Ray back when. And we realized the limiting case, the limiting feature in being able to estimate the minimum, it got much, much harder with a higher order polynomial because you have multiple minima actually. And so you actually don't know which one's the real minimum anymore. So it creates all kinds of bad problems. So if you went higher in this, you would just, this would just kind of fall here. Your search range would probably stay about the same, but the amount of noise you can tolerate would start to go down and down and down, just because you've allowed functions that are less smooth, essentially. Okay, so that's enough on the rough sketch of the theory side. What does this look like when you apply it? So for the first test cases that we did were flake-like molecules, but not trivial ones. We had a simple test case of benzene, but we applied it to larger molecules like coronene and also ovalene. Right, so these are fairly large. And shown here are the different structural parameters we considered. These are bond type parameterizations that we considered. In coronene, that's a 6-parameter model, and in ovalene, it's 19. So not tiny, not huge, but a respectable number of parameters you can handle all at once. This heat map just shows the coupling in the Hessian, basically. So that you can tell these modes aren't independent, and you can tell by looking at this plot that if you change one of these parameters, you're going to be affecting the other. So it makes sense that they're fairly tightly coupled. Okay. Before I go into the relaxation part, I'd just like to show that we can set tolerances differently for different parameters. So for example, the carbon-carbon bonds, you might want to know to 0.01, but the hydrogen-hydrogen distances, you know it's going to be looser and floppy. You can set a looser tolerance for those. There are 2 different methods of setting those constraints. I won't go into details of what those are, but there's a fixed point method, also a thermal balancing method that kind of distributes that among the different modes. Okay, but the actual line search, so if you look at slices through the potential energy surface along those conjugate directions, here's for coronene and ovalene, this is DMC data for each of those. So you can actually see the grid extent that was there. These points are the actual points at which you're doing a diffusion Monte Carlo calculation. And you can see some of these modes are very flat and shallow, and some are very stiff. And that's what you'd expect. Essentially, you know, the carbon-carbon bonds are these stiff ones. Carbon-hydrogen bonds are these slightly looser ones. And if you're looking at a distance parameter between 2 nearby hydrogen atoms, it's a very small effect on the potential energy to have them wave around. Okay, so what does that mean for the line search? What I'm showing below is a bar graph of the statistical cost per direction that's been optimized internally, automatically by the method through that correlated sampling approach that I explained before. And so these directions cost very little of the calculation, where these 2 dominated, right? So this is that hydrogen-hydrogen direction, this is a carbon-hydrogen, and some of these are carbon-carbon. So you're spending a lot less. If you had just said, well, let me spend the same everywhere, you'd be paying this much for all of them. And you can see, but by visually this area that's missing, there's a huge savings on the table there. And this type of thing is intrinsic to the problem, right? This isn't going to be different if you're using forces versus energies versus whatever. This is a property of the potential energy surface. With forces, you're going to be paying more along these soft directions too. But you may not be able to adapt for it, or where you can here. Okay, ovalene, you get a similar picture, except you notice there are a few of them that dominate. Some of these are just tiny compared to the rest. So actually, when we compare the actual overall statistical cost of performing the entire relaxation, it's something like a fraction of a millihartree on a single total energy calculation to do all of these calculations to the tolerance specified. So sometimes you can do this without paying a whole lot more than maybe just a slightly over-converged single total energy calculation. if you're careful. Okay, so let's see, I already went over that. So what's it look like in structural relaxation? These are plots of the 6 different structural parameters and the 19 different structural parameters as you evolve forward through different parallel iterations. These dashed lines are the tolerances which were set on them. So you can see the DFT structure is actually not so far away from the relaxed structure, right? Maybe 3 times your tolerance. But within an iteration or 2, you're there. And same thing for the total energy. It decreases within a millihartry and then fluctuates around. And so that's very near that ideal behavior that you would have even just in a noiseless case with slight enharmonicity, and you have the exact conjugate directions. Okay, now that might be expected, right? Because this is a hydrocarbon. PBE is not going to be terrible for a hydrocarbon, right? So maybe the directions are great. So how about something harder? So we go to quasi 2-dimensional materials, right? So these have, this is chromium triiodide, right? You've got transition metal elements. You've got different kinds of bonding here. It's going to be a lot harder than a hydrocarbon, in principle at least. So I'm going to show results from a couple of them. So here's the, for the germanium selenide monolayer. This is actually the very first system this method was applied to. And I'll show some justification for how the method works. So on the left is, so you have 2 structural parameters in this case, this A and B parameter. There's actually a third here, but I'll just show 2. So in the A and B parameters in DFT, here's a scan getting the actual potential energy surface. And here are the conjugate directions found by diagonalizing the Hessian. So you have a stiffer direction and one very soft direction. So germanium selenide, you can just stretch it very easily along one direction. Here's the DMC potential energy surface. So done with a whole lot of diffusion Monte Carlo calculations to raster this image out. So you can see where the minimum is. But these directions are still the DFT directions. You can see the minima are not close to each other at all. So in that sense, the PSs aren't that closely related. But in one way, they are closely related. If you notice, this minima in DFT is almost connected to the other one in DMC just by moving along this soft direction, right? So even though DMC has a huge error in the actual parameters and the actual structure that was found, it actually had decent information about how stretchy the material is in what direction. And so that allows you in diffusion Monte Carlo with the surrogate Hessian method to, in a step or so, walk right to the minimum, even though it's not close by at all. Okay, so as a second example, the chromium triiodide monolayer. In this case, we had DFT results. We did diffusion Monte Carlo on it. And later, STM measurements came out on the monolayer after we did our calculations. And so ex post facto, we were able to compare our results. In DFT, we were off on structural parameters about 2.4%. In diffusion Monte Carlo with line search here at 0.5% with an error bar about the same size. So pretty much exactly there. That's what you'd expect diffusion Monte Carlo to be able to do if you were actually sampling its potential energy surface. This method just allows you to do so. And we get about a 5 times reduction over the DFT errors. So this one I won't talk a whole lot about. I don't want to steal Jaron's thunder for tomorrow, but a much more interesting case was to apply this to vanadium diselenide in 2 different phases, one in an insulating phase and the other in a metallic phase. And we're able to get correct details about the metal insulator transition that are structurally dependent. So again, I won't steal the thunder, but I'll say we had a very successful application to this case as well. So kind of as a summary and outlook, methodologically, we've developed this method to be able to optimize structures. And this can be done for any kind of stochastic electronic structure theory. It doesn't need to be diffusion Monte Carlo. It exploits approximate but accurate Hessian information from DFT as a surrogate, but you could choose other surrogates that are cheap but fairly accurate. The method explicitly maximizes statistical efficiency while retaining controllable accuracy. You get to request what kind of accuracy you want, and that drives the cost. But on the method goes forward. And in practice, like I said, we've seen convergence in 1 to 2 parallel iterations from simple systems like benzene, chlorine, and ovalene, but also for more complicated ones like germanium selenide, chromium triiodide, and vanadium diselenide. So this is useful as a simple but efficient approach. And again, you can just put cell degrees of freedom handled as easily as others. It's going to be a while before the force techniques in quantum Monte Carlo catch up there. But we can do this today. Okay, as an example, so I'm not going to have you running diffusion Monte Carlo on laptops, in parallel line searches, but we will get to use the actual line search code to drive on a model system. Because again, this is just a method to minimize a stochastic noisy PES, along with as long as you have some information about it from somewhere else. So the type of so where is the actual code you use to run these methods? So this surrogate Hessian relaxation method lives in a repository under the main QMCPACK repository, just called Surrogate Hessian Relax. It couples with Nexus, so you can drive your system through this code with through Nexus directly. It's very easy in molecules, right? Because those calculations don't need anything additional. For solids, you might need to do some total energy, finite size corrections. If those are good enough, then great. Otherwise, you'll have to do some extrapolations, but that's kind of par for the course. But this is where the code is. You'll need to kind of do a git clone on this location. So for the workshop, if you just go in the workshop directory into day 2 Sur-Hess Relax, there's a README file. The system we'll be looking at is a simple artificial model involving 3 coupled Morse oscillators. So it's a 3-parameter system, but it does have anharmonic and off-diagonal coupling. And in this case, both the surrogate and the actual potential energy surface are represented by different but related coupled Morse oscillator systems. So you'll have deterministic structural relaxation along the surrogate PS is going to be performed by numerical methods in SciPy rather than in DFT. It's the same thing. You could use DFT structural relaxation. In this case, you're just doing a deterministic relaxation on a non-noisy deterministic PES. And then the full surrogate Hessian parallel line search algorithm, the actual one you'd use on quantum Monte Carlo, will be employed. But on this, on the actual PES with added statistical noise to represent diffusion Monte Carlo. So the requirements are pretty simple. You just need NumPy, DIL, SciPy, Matplotlib. You'll need Nexus, so you can git clone and put one Python path there. Same with Surrogate Hessian Relax. You git clone it, add a single Python path, and you'll be up and running. For the system itself, what to look for. You want to pay attention. It says I'm showing a cheat of the output here. I won't talk through it, but what you'll want to look for is the minimum energy parameters from the surrogate PES, details of the surrogate Hessian, kind of noting the degree of coupling between the modes, paying attention to where you define those user-defined parameter tolerances, watching the convergence of parameters with parallel iteration count, also noting the statistical uncertainty parameter for parameter. And then finally comparing it. In this case, since it's a simple toy system, I can create an analytic exact reference for where you should get. But to compare those minimum energy parameters with the DMC structure and paying attention to see whether your tolerances were obeyed, whether the answer stays within the parameter tolerances you asked for, both on the mean and including the statistical error on the mean. So if you do that, if you installed Matplotlib, you'll get a nice plot of the parameter convergence with iteration count and the total energy. And that lab is available to you now and throughout the day. Feel free to ask me questions about it as you try it out. With that, I'll just acknowledge kind of funding through the CAPMS, and I'll take any questions that you have on this topic.
That's a great presentation, Jaron. Open for questions.
Hello, I'm Igor from University of Delaware. So this was the first time I was introduced to this method. So thank you for the talk. It was really nice. And I might have like a naive question about it. 2 questions actually. So this method you're showing for the solid part applied to 2D materials, which we can. So let me ask the easier question first. when you do the lattice parameter optimization, you show how to do that, but you also relax, you can do optimization of the atoms positions or?
Yeah, so some of those relaxations were internal coordinates and cell parameters simultaneously.
Oh, nice. Okay. Oh, that's related to my second question then, because I was gonna ask, because you're just showing the 2D materials, which you can construct with hexagonal cell, which has just one lattice parameter. But how about more complicated crystal structure like monoclinic? Can you do multiple optimization of the lattice parameter, including the angles between
Yeah,
vectors?
yeah, you can. And we actually demonstrated in the simple molecules case, at least in the paper, the original paper, that you can do different parameterizations. So in that case, you have choices like you can do parameterizations based on the bond lengths or bond angles. The method can work. So in crystals where you have both lattice parameters in terms of distance quantities and angular quantities, those all are included. All the method knows about is that you have a parameterization that is living in some nonlinear space, and that it gets the Hessian within that nonlinear space. It doesn't need to know more than that, but yeah, it can handle those cases too.
Thank you.
Great talk, Jaron. Do you think that this can be extended to materials under pressure in some way?
Yes, I think it could, but you'd have to introduce something additional, I believe. You'd probably be the function that you're optimizing and the constraints you impose would become a little more complicated, but that would be a very interesting extension to the method. So if you have ideas along those lines, yeah, let's talk.
Maybe one day.
Maybe one day soon. Questions? Okay.
So I have two questions, Jaron. So the first one is there a way to formalize how accurate the surrogate PES needs to be in terms of curvature and position in order for this to work?
So that's an interesting question. So one reason why I built it on top of line search methods is because they're essentially, you can consider those being tough as nails, more or less. So if you, a class of line search methods related to this is like Powell's method, where you don't really know anything about the directions to start with. You're just doing line search scans. Those will eventually converge, right? It may just be slow. So as the directions become imperfect, if they become very imperfect, it will affect the efficiency, right? So you'll start to have to take more iterations to get to the minimum. And that's how you'd see it appearing in this method, is if you see it taking 4, 5, 6 iterations, you'll know your search directions from your surrogate are somewhat mismatched to the DMCPACK. If they're totally unrelated, it might take 30, 50 iterations to converge if it's just total junk. But we're also using the information from the surrogate to set these parameter tolerances, right? Because that's all done with prior information before you begin the run. And so that could be violated. If the surrogate's terrible, then their tolerance you asked for might result in a parameter that you get out being either much tighter than you thought or looser than you thought. So we are leaning a little heavily on the surrogate for that purpose. I would say if you find that to be the case, you can just tighten your tolerance a bit and rerun and see if anything significant changes, right? If you want to really be inquisitive about it, that would be the approach. But following that, yeah, no, it should systematically converge, provided the directions aren't just totally wrong.
And my other question is, in one of your final slides, you showed for the Morse potential, the converging energy and the parameters. Could we go to that? Yep. So if you zoom in on the last 4 iterations of the energy, you will notice that it actually goes up very slightly, or it bounces around. At least that's what I noticed, in some of my cases.
Mm-hmm.
So what's the correct way to explain it not immediately converging and staying at the energy minimum?
So what it should do let's see, so here, right? It should fluctuate around the energy minimum. So the method doesn't work within an energy tolerance. It's actually based on parameter tolerances, but those will necessarily impose a type of energy tolerance. But if you see the energy go up, it really should be based on the statistical fluctuation. You'll notice some of these are up relative to the others. It should just not be statistically significant. If it is statistically significant, then there are other issues at hand. But again, the convergence is really on the parameters, right? And so what you really have to watch is that the parameters themselves don't fluctuate well out of some equilibrium there, right? Because these are subsequent calculations afterwards at these points. So I could choose whatever energy tolerance I wanted, right? So I could, if I wanted to, expose the actual differences between these, because they are different, right? You have a stochastic fluctuation around the minimum, but it's not meaningful at the scale which I asked for the parameters.
So you would expect that even if it was a noisy, noiseless search?
No, it's a product of the noisy search. So you have you basically have the statistical fuzzy object, which is the PES. And so any information you have is also fluctuating about its minimum.
Hi, Jaron.
Hi.
So I have a question. How can we also accelerate this process by avoiding, let's say, finite size convergence for the crystals? So let's get one large cell, and instead of doing smaller.
So that's a great question. So what you need is to be able to be close enough to the thermodynamic limits answer, however you got it, that you're happy with the results, right? And that can be done either through a large enough cell, which you'll pay a lot for, or better yet, we have a finite size correction scheme, which is robust and accurate, that can be applied everywhere. Now, there've been developments in that area. On the theory side, I think implementation-wise, there's still some work to do to get those fully implemented for QMCPACK post-processing. But it's been shown that we can run with those corrections in fairly small cells and get close to the thermodynamic limit in one shot. And so that would be the ideal, is that these finite size corrections become fully productionized, and then we can run in maybe not a primitive cell, but like a 2x2 kind of cell that's cheap enough for a small cluster, and then just do a one-shot calculation. So that would be where I'd put the priority, because I agree with you. If you have to do finite size extrapolations for every single point that you do this way, it just gets painful.